Hello AP Chem students and welcome to topic 6.2, energy diagrams. The learning objective for today is 6.2.a, represent a chemical or physical transformation with an energy diagram. So we've looked at energy diagrams before. So the energy change in a physical and chemical process can be clearly seen by looking at a diagram like this. All right, so we talked about these in kinetics and looking at activation energy. We looked at how it's impacted by having a multi-step reaction or by using a catalyst. So today we're going to be focusing on the thermodynamics or the thermochemistry of the reactions. So if these are your diagrams, we can get several types of a piece of information here. So first of all, what type of reaction is it? So when the products end at a point that is higher than the reactants in terms of their energy, that makes it an endothermic process. And you can see that here. Now, when your products end up lower in energy than your reactants, that is an exothermic reaction. And so your sign of delta E for endothermic is positive, which we already discussed in the endothermic and exothermic video before. But now it's clearly easy to see that because if you do a products minus reactants calculation, this is a higher value than this. And so this would be a positive delta H that would be required to increase the energy from reactants to products. Versus exothermic, your products are at a lower energy than your reactants, and so that extra energy will be released. And when energy is being released from a system, that makes it exothermic, and it has a negative sign. So then again, just to reiterate, the products here are at a greater energy. So there's more energy in the products in an endothermic reaction than there is the reactants. And there's less energy in the products of an exothermic reaction. Students often get these confused because they're so used to thinking about exothermic reactions releasing heat, and so they think that makes them have more energy in the products, but actually the heat that's being released is the excess energy that is not contained in the products, right? So the reactants are at a higher energy, it goes through the transition state, the products are produced, and because these are at a lower energy, that difference in energy is released in the form of heat to the surroundings. So I have a practice problem for you here. So if you want to try it first, go ahead and pause the video because I'm just about to show you the answers. So the enthalpy of the reactants in this situation is about 80 kilojoules. You can see that on the graph. The enthalpy of the products is going to be there, and so that's going to be about 160. The activation energy is at the top of the curve, so that's a little bit of review from last unit. That's going to be up here at, so this is your, the height up here is your transition state. So to find the activation energy, you would take the energy at the peak, which is 240, and you would subtract the energy of the reactants. And so that would be 240 minus 80 is 160. So that will be your activation energy. The heat of the reaction is going to be your products minus your reactants. So we're going to do 160 minus 80, and that's going to give us 80 kilojoules for your overall delta H for the reaction. The forward reaction is going to be endothermic because your products are at a higher energy than your reactants, and the enthalpy of the reactants is less than the enthalpy of the products. And that is that. So what should you be able to do with this? You should be able to interpret energy diagrams, specifically identify the reactants and products as which one is higher in energy, okay? Determine if it's endothermic or exothermic by looking at the graph, and calculate delta H from the values on the graph if they're given, and that is it. And you should also be able to calculate activation energy as well. So that's it for that topic, and I'll see you soon for topic 6.3.